Sonic log is one of the most important logging tools that we deal with in formation evaluation because not only this logging tool is used in order to estimate the primary porosity, that is very important property of the formation, but also it is widely used in order to interpret seismic data. And that's the thing that I think it is very important to understand how this logging tool works. Sonic log measures the seismic wave travel time in the formation. So this logging tool has a source that produces some seismic waves and also has some detector or receivers that record those waves. Indeed, we deal with seismic waves in our daily life. For example, the acoustic wave or sound wave that we deal with in our life, and this is how we are able to communicate with each other, is subcategory of seismic waves. So indeed, our larynx is a kind of seismic source that produces some seismic signal, and our ears are two seismic receivers. So indeed, seismic waves is a kind of mechanical wave that propagates through a medium, and it can be divided into two categories. The first category of seismic wave is kind of body wave. Body waves are those waves that can travel through the earth, and this is how we are able to obtain some information about deep structures such as inner core, outer core, mantle. And also another category of seismic wave is a kind of surface wave, seismic surface wave, as we see here. And seismic surface waves propagate along the Earth's surface. And this is how we are able to obtain useful information about shallow formation, for example, near surface. Seismic body waves can be divided into two subcategories of primary or P waves and secondary or S waves. And as you see here, P waves are kind of longitudinal. It means that the particle motion is parallel to the wave propagation direction. On the other hand, S wave is a kind of transverse. It means that the particle motion is perpendicular to the wave propagation direction. So here you may ask me why we call it like P wave or S wave. That goes back to seismology. So in seismology, so whenever an earthquake happens, for example, here, and then assume that you have a seismometer far away from the earthquake, what seismologists observe, they observe two groups of waves. The first group of waves that come to the recording station first, they call it P wave. And P wave is kind of high speed or high velocity seismic wave. So they have the highest speed, and that's the reason they get to the recording station first. And after the first group of the waves, they notice another group of the wave that come later, and they call it secondary or S wave. And the reason why they come after P wave because they travel more slowly compared to P waves. Surface waves can be, again, divided into two subcategories. Rayleigh wave, as you see here, that is produced as an interaction of P wave and S wave. And as you see here, it has retrograde motion. And we have lobe waves. Lobe waves is a kind of S wave that is trapped in near surface formation. And as you see, lobe wave similar to S wave is kind of transverse. It means that wave propagation direction is perpendicular to the particle motion. If I want to talk about the speed of seismic waves, as you see here, the P wave travel faster, and after that we have S wave, the lobe wave, and Rayleigh wave. So when we want to compare the speed of different seismic waves, I can say that the Rayleigh wave has the slowest velocity and the P waves have the highest velocity. In well logging, because the goal is to measure the seismic velocity within the formation, Usually, we use P-wave in order to characterize the formation. However, there are some logging tools that also measure the S-wave velocity within the formation. But I can say that P-wave is more popular because it is much easier to produce, it's much easier to record. However, it doesn't mean that S-wave is not useful. S-wave can provide a lot of information, in particular about the fractures, their orientation, their intensity in the formation. So that's the thing that companies are investing a lot to develop logging tool for S-wave. But as I said, P-wave also is very interesting. And in this lecture, I'm going to focus on P-wave. So the seismic velocity of P-wave is given by this equation. And here K is incompressibility or bulk modulus, and mu is rigidity, and rho is density. So what is bulk modulus or incompressibility? Indeed, bulk modulus is resistance of material in deformation in volume. Okay, so for example, assume that we have an object and we apply pressure on the object. So we know that the volume will decrease. So if assume that we measure this ratio, delta P is the exact applied pressure to the object, and delta V is the change in the volume over the initial volume, then we're going to have this equation to obtain bulk modulus or incompressibility. So, for example, when we deal with a rock that highly resists deformation in volume, we're going to have high incompressibility. Now consider, for example, gas. If you apply a little bit pressure to gas, you're going to see significant change in the volume. So it means that gases are, in general, have very low incompressibility. And shear modulus is the resistance of material to deformation in shape. So we know that, for example, gas and liquid has zero rigidity because they don't resist deformation in shape. And then we talk about solid materials. So the more resistant the solid material in deformation in the shape is, then we can say that that material should have higher rigidity. And also mu is called sometimes shear modulus as well. Now let's look at the equation for P-wave velocity again. If you look at this equation, you may notice that if we look at different rocks, so we should expect that rocks with higher incompressibility and rigidity should have higher P-wave velocity. But what do you think about density? As you see, density is the denominator here. So what do you think about that? So do you think that dense rock should have lower P-wave velocity or not? So something that is tricky here is that usually denser rocks have much higher incompressibility and also rigidity. And that's the thing that although rho is denominator here, incompressibility, higher incompressibility and rigidity somehow mitigate the rho being the denominator here. And indeed, there is a law or Gardner's law. What Gardner did, he collected different rock samples and then he measured their seismic velocity in the lab and also their density and plot these values along each other. And what he found this curve. So, and here is velocity, the y-axis is velocity, kilometer per second. And as you see here, the horizontal axis is density. So as you see here, if we look at the relationship between different rocks, their velocity and density, you may notice that by increasing the density, the seismic velocity increases. And this equation that you see here shows the relationship between density and seismic velocity. This equation was developed by Gardner, and it's a kind of an empirical equation. So when we look at a rock is composed of two parts. the matrix part and the fluid part. And in general, doesn't matter what type of matrix that we have, usually the velocity of the matrix is much greater than the velocity of the fluid part. Now, when we talk about the fluid part, the fluid can be water, can be oil, and can be gas. And as you see here, the seismic velocity in the water is greater than oil, and that is greater than gas. So this is something that we should consider when we talk about rock that is saturated by some kind of fluid. Okay, so when we talk about the rock, so if we have the matrix velocity here and the fluid velocity here, so for a porous rock, the average velocity of the rock lies between the matrix velocity and the fluid velocity. And indeed, there is an equation that was developed by Wiley. So, and it's called Wiley's time average equation. And what Wiley did, Wiley collected some rock sample, and he mostly worked with consolidated rock samples, and he measured their velocity and also their porosity with respect to specific fluid that can be, for example, water. And what he noticed, he was able to obtain this equation or this relationship that links the seismic velocity, the average of the seismic velocity, to the porosity and matrix velocity and the fluid velocity. So it is called Wiley's time average equation. Something that you may notice here that, so whenever the fluid contribution becomes bigger in this averaging, so it means that the seismic velocity should decrease. And this is something that we can infer from Wiley's time average equation. So Wiley's time average equation says that once the porosity increases, because we're going to have more contribution of the fluid velocity to the average velocity, so the average velocity of the rock should decrease. Now assume that we have like sandstone, and for sandstone the matrix velocity is 5,400 meters per second, and assume that the fluid is water with the velocity of 1,500 meters per second, and assume that the porosity is 30%. So if we have that, how much is the average PV velocity in that rock? Yes. So if just you use Wiley's time average equation, then you're going to notice that the average velocity will be 3,000 meters per second. Now let's rewrite the Wiley's time average equation again. So we know that velocity is given by x over t. X is the distance and t is the travel time. And now assume x is kind of the unit of length. For example, it can be 1 foot or it can be 1 meter. Okay. So if you assume that x, for example, to be 1 foot, the unit of length, then we're going to have velocity is equal to 1 over t, and t is the travel time of seismic wave over 1 foot. So in such a case, then I can say that t is equal to 1 over v, and then I can rewrite the Wiley time average equation in terms of the travel time. So why I rewrite the Wiley's time average equation in terms of the travel time? Because indeed, sonic log measures the travel time in the formation. So travel time, if you have the travel time, the reciprocal of the travel time, or as you see here, 1 over t gives us the p-wave velocity. So this is how we are able to obtain the p-wave velocity from the travel time. But indeed, what is measured by sonic log is the travel time, of seismic wave per unit of length in the formation. Having said that, then we are able to obtain porosity from the travel time of seismic wave using this equation. Here, t is the travel time that we measure by the sonic tool. TMA is the travel time over the matrix. And as you see here, for different rocks, we have different travel times. For example, for sandstone, the travel time has a range from 51 to 55 millisecond. For limestone, 43 to about 47, and etc. And for the fluid, if the mud filtered is fresh water, so TF will be 189, and if it is saline water, so in that case we're going to have 185. So as you see here, this equation, if you have some idea about matrix, and also if you matrix of the formation, and if you have some idea about the mud filter, so if the mud filter is fresh water, or if it is like saline water or brine, then we are able to use this equation to estimate the porosity from sonic log data. Different logging tools, sonic logging tools are available. So one of them, for example, as we see here, is a borehole compensated sonic log. I'm going to explain how this logging tool works. As you see, this logging tool is composed of, indeed, two transducer, lower transducer and upper transducer. And these transducers are kind of seismic sources that produce seismic signal into the formation. And here you see R1, R2, R3, R4. These are like 4 seismic receivers that can detect and record seismic signals. And something that you may notice here, the distance, for example, between R2 and R1 is X, and the same for R3 and R4. So the distance is X. So how does this logging tool works? First of all, like the lower transducer produces a seismic pulse that propagates through direction in this geometry. So as you see, the geometry is kind of trapezoidal, and why we have such a geometry, it can be explained by a Snell law that is beyond the scope of this presentation. But, like if you look at any book that talks about seismic wave propagation, and if just you read the section about Snell law, then you can easily understand why we have that geometry. So indeed, here we're going to have two recording time. So one of them is T2, that is the travel time that is recorded by R2, and T1, that is the travel time that is recorded by R1. So if we calculate the difference T2 and T1 and divide it over X, that is distance between R1 and R2, then we are able to obtain the travel time per unit of length. And so I indicated here by T prime. And after that, the upper transducer produces another seismic signal that is recorded by R4 and R3. Again, what we do here, we measure the difference between R4 and R3 and divide it over X to obtain the travel time per unit of length. So if there was no noise in the borehole, and assume that if the formation was homogeneous, okay, T prime and T double prime should be equal. So if there was no noise in the formation, or the formation was 100% homogeneous. But in reality, they are not. They are not equal because we have some noise in the formation. So by calculating their average, somehow we want to mitigate the effect of the noise and also heterogeneity of the formation to obtain a more accurate estimate of T in the formation. Something that I forgot to mention, it is like kind of seismic pulse that is produced by lower or upper transducer. The seismic pulse that's produced has like shape like that. So something that you may notice here, the borehole environment is noisy because, so whenever we have some borehole data acquisition, so the sound move into the borehole, and as a result, it produces some noise. In addition, we have on the surface facility, we have some workers that are working at the same time. So as a result, the borehole environment is noisy. And that's the thing when, for example, we look at like sonic log data, we may see such jumps like that. And these sudden jumps that we may see, it's possible that it's because the effect of the noise that somehow has degraded the data. And this is how different methods have been developed in order to cancel the effect of the noise. Now just let's go back to the seismic record that I showed here. So what you see here in this track, you see the value of the sonic log. And as I said, these jumps can be related to the effect of the noise. But something that you may notice here, the labeling is 40. For example, microsecond per foot to 200 microsecond per foot. And something that is interesting here, you see that the general trend of the seismic travel time is decreasing with depth. So what we can infer from this observation, we can infer that the seismic velocity increases with depth, and that's the reason we see lower travel time in deeper sediments. And it is something that is consistent with different experimental observations. There is no theoretical equation in order to link the seismic travel time to porosity. And all of these equations that we use are some empirical. For example, Wiley's time average equation is empirical. And Wiley, as I mentioned, developed his equation based on some rock samples, consolidated rock samples. Which means that Wiley's time average equation just works for consolidated rock. So for example, if our formation is unconsolidated, we may not be able to use Wiley's time average equation. And the reason, because of two factors. The first thing is that usually when we talk about consolidated rocks are deeper, and the seismic velocity increases with depth. Indeed, assume that this is a part of the seismic rock that we have, and you see between the grains there is a mechanical continuity, and so the more pressure that we apply, the overburden pressure that we apply to the grain, these grains are somehow will touch each other better, or we're going to have a better mechanical continuity, and as a result we're going to have much higher P-wave velocity. Another thing that consolidated rocks are usually older, and that's the thing. There is sometimes for mineral to develop here, or we're going to have some cementation between the grains, and that cementation somehow enhances the mechanical continuity. And indeed, there is an equation that is called Faust equation, and Faust equation says that the seismic velocity increases by depth, that is z here, and t, that is time. And that's the thing. So when Wiley developed his equation, as I said, he worked on just consolidated rocks. So consolidated rocks have higher P-wave velocity compared to unconsolidated rocks, or they have shorter travel time compared to unconsolidated rocks. And that's the thing. If you want to use Wiley's time average equation for unconsolidated rock, then we're going to have a lot of error in calculating the porosity. So just let me ask you a question. So as I mentioned, Wiley's time average equation is empirical, and it was obtained for consolidated rocks. So what do you think about the estimate of porosity if we want to use Wiley's time average equation for unconsolidated rocks. So do you think that the porosity will be overestimated or underestimated? Just look at this equation. So the answer is that if we deal with unconsolidated rocks mean that the velocity is lower or t will be greater than consolidated rocks. So if we put a greater t than what is supposed to be in the equation, we're going to obtain an overestimation of the porosity using sonic log data. And this is something that we should consider. So Wiley's time average equation is an empirical equation that was developed just for consolidated rocks, and it doesn't work for unconsolidated rocks. So in other words, if we deal with near surface formations, definitely we shouldn't use the Wiley's time average equation in order to calculate the porosity, because we're going to have a lot of overestimation of the sonic porosity. Wiley's time average equation was developed based on consolidated rock samples, so it just works for consolidated rocks. So here is the question. What we can do if we deal with unconsolidated formation? So in order to address this problem, petrophysicists try to develop different approaches. So one of them was to apply some correction factor to the porosity. So what they propose is that assume that we have a like shale formation close to the unconsolidated formation. So what we do here, we measure the seismic travel time within the shale formation and we divide it over 100. And in that case, we're going to obtain a correction factor that is shown by BCP. And what we should do is just, if we divide the sonic porosity over the correction factor, then we may be able to obtain a more accurate estimate of the porosity. So this is one of the approaches that was proposed by petrophysicists in order to somehow have a more accurate estimate of the porosity using Wiley's time average equation. So just let me give you an example. So assume that we deal with an unconsolidated formation and the measured seismic travel time is 143 microsecond, and TMA is 55, TF is 189, and the travel time in the shale formation is 145. So how much is the porosity, the correct porosity after applying the correction factor? Okay, so if you just do some calculations, you're going to obtain the porosity to be 45%. Something that I want to emphasize here, what you're given is like from a real scenario. And indeed, the formation that just I'm talking about had the porosity of about 37%. But as you see here, after even applying the correction factor, you're going to get 45%. So it means that still the porosity is not that accurate. If you didn't apply that correction factor, the porosity that you would have calculated would be 66%. That is so off the correct porosity. So it means that, as you see, applying the correction factor we may help us to obtain a more accurate estimate of the porosity, but still it's not that accurate. So what we can do if we deal with unconsolidated formations? So the good news is that some other equations that are available, that are developed for unconsolidated formations. So we may use those equations in order to obtain a more accurate estimate of the porosity for unconsolidated formations. So here is the thing. So if we want to use sonic data, okay, in order to estimate the porosity, not only we have to have some idea about the fluid in the formation, the lithology, but also we should have some idea about the state of consolidation in the rock. So if the rock is consolidated, we may use, like, for example, Wiley's time average equation, or if it is unconsolidated, we may use other equations that are developed for unconsolidated formation. So this is something that you should notice. As you see, compared to, for example, density log, that just we needed to have some idea about lithology and also the fluid in the formation. For sonic log, if we want to extract information about the porosity, in addition to the lithology and the fluid property, we also should consider the state of consolidation of the rock. So here, another important consideration is the fluid in the formation. Something that you may notice here, if we deal with like oil and gas reservoir, oil and gas is are general have much lower incompressibility compared to water, and as a result, if we have some hydrocarbon saturation in the formation, the seismic velocity should decrease in the formation. What you see here, this plot shows the seismic PV velocity. The dashed line is for oil, and the solid line is for gas. And here shows the water saturation. So here on the right, we have 100% water saturation. It means that the hydrocarbon saturation is 0. And here, the water saturation is 0, or the hydrocarbon saturation is 100%. So what I mean, if we have a rock and then just if we have some experiment, in the beginning, we saturate the rock by water 100%, and then measure the seismic velocity, and then gradually decrease the water saturation and increase the oil saturation, we're going to end up a curve like that. So this curve says that, okay, the seismic velocity decreases with oil saturation. And the reason, because the oil has much lower compressibility compared to water. So whenever we displace water by oil, then we're going to have that situation. Another thing that you may notice here, but for gas, the situation is a little bit more dramatic. Once we inject a little bit of gas into the rock, a little bit of the gas causes huge drop in the seismic velocity. And the reason, because gas has much lower incompressibility compared to water. So now let's go back to our equation that you see here, for the seismic velocity that we have. So we learned that this is the equation for seismic velocity in a rock, and here K is incompressibility and U is rigidity. So what I'm saying, that once we inject a little bit of gas into the rock, incompressibility of the rock will drop significantly, and that's the reason we see that huge drop in the seismic velocity. But as you see here at a specific saturation, you see that after that specific saturation, the seismic velocity increases a little bit. So you may ask me why, when we inject more gas into the rock, we don't see the seismic velocity drop significantly. And the reason, once we inject more gas, the K will not decrease that much. So in other words, the drop of the incompressibility of the rock is sudden. So once we inject a little bit of the gas, that drop will be significant. And by injecting more gas into the formation, the K will not reduce that much. So in other words, the K will get to its plateau, the minimum value. But so once we inject more gas, so the density of the rock will decrease. So that's the thing, because here X is denominator here. So once the because rho is the denominator here. So once we inject more gas into the formation, rho decreases. So as a result, it gives a little bit rise to the seismic PV velocity. So that's the thing. You see that after a specific gas saturation, the seismic velocity increases for gas-saturated reservoirs. So don't get confused. Something that just I want to show here is that doesn't matter if we have hydrocarbon is oil or is gas, the seismic velocity is much lower in the formation compared to a water-saturated formation. And this is, again, another thing that makes the estimation of the porosity from sonic data challenging, okay? So for example, if you remember from my lecture about like density log works, it's not that inaccurate for oil saturated formation, the same for neutron porosity. But as you see, when we deal with like sonic log, definitely again, we have to make sure that the fluid type, so if it is oil or if it is gas, and that's the thing makes the process of calculating porosity from sonic data more challenging. You may have noticed that estimation of the porosity from sonic data is not that straightforward. It's very challenging, so we have to consider so many factors. We have to have some idea about lithology, the fluid in the formation, and also the state of consolidation, if we have hydrocarbon or not. So it is a lot of challenge. And the equations that have been developed in order to estimate porosity from sonic data are empirical. So it means that they may work for a specific group of rocks. And despite of these challenges, still we are interested in estimating the porosity from sonic data. So here you may ask me why. So in order to answer you this question, just let me talk about the porosity itself. Indeed, when we talk about the porosity of the rock, the porosity can be divided into two, into two parts, I can say. The first part is the primary porosity. So the primary porosity of the rock is the porosity of the rock when it forms. So indeed, it refers to the space between the grains. And then we have secondary porosity that comes from fractures. So when the rock is formed and as a result of tectonic activity or stress or different things, it is fractured. And then we're going to have additional porosity to the rock that is called secondary porosity. So indeed, the porosity that we measure in the rock is a combination of primary porosity plus secondary porosity. And indeed, the velocities that we measure by density log and also neutron porosity log are the total porosity, means that secondary plus primary porosity. However, different observations have shown that the sonic porosity is insensitive to the secondary porosity. So in other words, the porosity that we measure from sonic data is just only primary porosity. And that's the thing that makes sonic porosity so interesting, because sonic porosity just gives us some information about the primary porosity. So if we compare the sonic porosity with the total porosity that we get from, for example, density and neutron porosity data, then we are able to have some idea about the presence of fractures in the formation. So indeed, in general, phi dn, which means that the porosity that we get from the combination of density log and neutron porosity log usually should be greater or equal to the sonic porosity. So if the rock has no fractures in it, so in that case, the sonic porosity should be equal to the total porosity of the rock. But if there are some fractures, in that case, the sonic porosity will be smaller than the total porosity of the rock. And indeed, one index has been introduced, and it's called secondary porosity index, that is given by this equation. Phi dn, as I said, is the total porosity that we obtain from density and neutron porosity log data, minus phi s over phi dn. So this is called secondary porosity index. That is a measure of fracture in the formation, presence of fracture in the formation. So for example, if SPI is equal to 0, it means that there is no fracture in the formation, and all the porosity that we have is a kind of primary porosity. But if, for example, SPI is equal to 50%, it means that like 50% of the porosity of the formation comes from primary porosity, and 50% comes from fractures. So why it is important? Because in particular, when we talk about carbonate rocks, limestone, dolomite, the permeability is low in those formations. And if you have some fractures, fracture can enhance the permeability significantly, and as a result, we're going to have better production from the reservoir. And that's the thing, that if you have some idea about the presence of fracture in those rocks, it's going to be, I can say that, invaluable information for us. And that's the thing, if we have, if you're able to measure the secondary porosity index, so it is very important, I can say that, piece of information that we can get from sonic data. And that's the thing makes the sonic porosity so valuable. So sonic porosity can help us to have some idea about the presence of fractures, the percentage of the fractures in the formation, that is so critical for carbonate reservoirs in particular. So now assume that phi d is 30% and phi n is 27, and the sonic travel time is 60.47, matrix 38.5, and fluid 185. So how much is the secondary porosity index? So in order to make it easier for you, phi dn, or the total porosity, is given by phi n plus phi d over 2. So the answer is 0.25%. So it means that 1/4 of the porosity comes from fractures. Something that, again, we should notice here is the limit of each logging tool that we use, a sonic logging tool that we use. And that's the thing, that the limit of a sonic log depends on x. Okay, so it means that the greater distance that we have between the receivers, then we are able to somehow measure the seismic velocity in larger diameter boreholes. For example, if like x is just 3 feet, the maximum borehole diameter of the borehole that we can measure the seismic velocity in it is about 14 inches. So it means that if the borehole diameter is greater than 1, it is possible that the seismic wave cannot penetrate into the formation, and as a result, we are not able to measure the seismic travel time in the formation. So in other words, if we deal with borehole with larger diameter, definitely we have to make sure that the distance between the receivers is large enough so they can measure the seismic travel time into the formation. In order to measure the seismic travel time in large boreholes, different logging tools have been developed. And one of them, for example, is large spacing sonic log. And as you see here, this logging tool is composed of 2 transducers and 2 receivers. T1 and T2 are 2 transducers, and R1 and R2 are 2 receivers. And as you see here, the distance between the transducers and receiver are so large. So in order to be able to measure the seismic velocity in large borehole. So assume that here is the borehole wall. And we want to measure the seismic travel time at point A. So what we do here first, T1 or the first transducer produces a seismic signal that is recorded by R1 and R2. And what we do here, we measure the travel time between T1 and R1 and T1 and R2. So the difference of the travel time of R1 and R2 is recorded and is sent to the memory of the logging tool. And then once the transducer, the two transducers arrive at B, again, we're going to have another pulse. These two transducers produce pulse simultaneously that are recorded by R2. Then we're going to have another travel time, T2 R2 minus T1 R2. And this travel time is somehow averaged with the travel time that was measured before in order to somehow cancel the effect of the noise and the, heterogeneity of the formation in order to have a more accurate estimate of seismic travel time in the formation. So this is how this logging tool works. Okay, so as we see, it uses some short-term memory in order to measure the seismic velocity at different locations along the borehole. I hope that you have enjoyed the lecture. So in this lecture, I talk about how we may use some empirical equations in order to estimate sonic porosity from sonic data, and why this is important, because sonic porosity provides us with some information about the primary porosity, from which by comparing the sonic porosity data with the total porosity data, we are able to have some idea about the presence of the fracture and level of fracturing in the formation that is so critical, in particular when we deal with low permeable formations such as carbonate formations. I hope that you have enjoyed the lecture. Thank you very much for your attention.